All right, so take the big slice of paper and fold it so you kind of, it doesn't have to be perfect thirds, but fold it into three parts. And then what I want you to do is on page 22 in your notes, write on the big slice on here. We're going to take this page of notes and lay it out bigger so that you can see it. Traditionally, this section on linear approximations has been difficult. It went far better last hour than it's ever gone, and I think it's because we really took the calculus and just went algebra right away instead of to a calculus formula, and that's what I'm going to have you do on the big slice first. So fold it into thirds. I'll go grab a big sheet of blank paper. If you're watching this on video, just grab a blank sheet of white, like printer paper, and fold it into three pieces. On the top third, what I want you to do is cover the top third of that sheet of paper with a graph that kind of stretches out. I want the graph to be bigger than it would be in your notes. I want you to see what you're doing so you don't have to memorize anything. So on the top third of your paper, let's put a fake function. So just go like this. I'll wait for you. Top third, we'll put a graph. Middle third, we'll put the formula. The bottom third, we'll do a little analyzing. It went really well last hour laying it out like this. I think it helps to see it before we do it. What I want you to do is label this x, this f of x, and in the top right-hand corner, write linear approximations. And then we'll write, also known as, because sometimes they're called tangent line approximations, so we'll put it both of them on here. Also known as tangent line approximations. Just put that in that top corner. I'm going to put it on a graph first, and then we'll go get, if I just give you the formula, it's got a bunch of c's and f primes of c's and x minus c's, and it won't make sense. So we'll derive the formula first, then you won't ever have to memorize it. So what I want you to do on your graph is I want you to go put a little spot here on the x-axis called c. Then go up to your curve and nail that curve, and we're going to label that point. Obviously, it would be c, right? And then comma, what would the y value be? F of c, yeah, perfect. So in the formula, you're going to see c's and f of c's. Really, it's just a point on the curve. You will be given it, so it won't be any issue to find. You'll at least be given the x, so you can plug it in to get the y. So you're going to have a point on the curve. And the theory behind this is that if you draw the tangent line, draw it nice and neat and kind of lengthen it out here as best you can. When you draw the tangent line at that point, when you're really, really close to c, f of c, so go put some little brackets on there, the red tangent line and the curve are about at the same heights. So what a tangent line approximation does is we come up with a formula for this red line. And as long as we stay really close to this point of tangency, if we don't veer off like way over here, because right here there's a huge gap between the curve's y values and the line's y values. But as I get closer to that point of tangency, these get closer and close together, and right next to it, they're darn near the same. Would you agree with me? So the theory behind it is if you could get an equation for the red line, you really know what's happening on the curve as long as you're really close to that point. Historically, what it was used for, when I was in math, we didn't have, well, I'm still in math, but when I was in high school, we didn't have like calculators that you could just go do the sine. We're going to do this one in a little bit. Sine of 1. Go do it on your calculator, by the way. Just go sine. Make sure it's in radians. And you guys have it easy because you just have a calculator that you just get to go hit sine 1. I didn't. My calculator had addition, subtraction, multiplication, division, a clear button, kind of like the kind you get in a cereal box, basically. But go hit sine 1, and what do you get? Point. I think 841. All right. In about 10 minutes, we're going to get 0.84 without ever even using the sine curve. We're going to use a line. And when I was in high school, what happened was when I wanted to do the sine of 1, I had to go to a table in the back of my book, and I'd have to go down to 1 radian, and then I'd run sine, cosine, and tangent. It wouldn't have the other 3 because you can get those, you know what I mean, all the trig functions you can get from those main 3. So I'd have to read a table, and then I'd have to go pluck this off the table. But the person who made the table didn't have a graphing calculator either. How do you think they got a number there? This. Okay, so it's got historical value that's kind of since gone by the wayside because we have these fancy calculators, but we are going to use the process. So what we're going to do is somehow use this line to approximate what's happening on the curve. And as long as we're close, we're good. So draw yourself in the middle third. This is the formula you would see in your book. It's all about a line. And what form of a line do we use in calculus exclusively? What form do we always get it in? Point, slope. So it's actually, the formula is really point, slope form of a line, which we know. It says this: the equation of this red line would be y minus the y I know, which is f of c, is equal to the slope there. What's our calculus word for the slope there? The tangent. Yeah, exactly. So we'd say f prime at c. It's really just the slope of the line times x minus c. This is really point slope form of a line. Y minus y is equal to the slope times x minus x. The way you'll see it in any textbook is they will take this subtraction of f of c and they'll add it to the other side. So if you were to look in your book, I think this is 3.8, you'll see an f of c, because they're going to move it over, plus f prime of c times x minus c. Next, usually what they do is they don't call it y. They call it L of x for linear approximation at x, or they call it T of x for the tangent line. I'm fine with you leaving a y. It'll serve your purposes well, and you won't ever lose any points for doing that. So I'm trying to scroll my screen, but I'm not seeing my scroller. Oh, there it is. It's over here. All right. So, oh, that's not the one I want. Help me out, guys. Do you see my... I can't scroll. All right. Well, whatever. So, well, I want to move. There's a thing down here that allows me to extend my screen, but I can't. Let me see if I can. I'm making it worse. I'm just going to leave it. So anyway, a lot of times in a book, you'll see this is written like L of x or T of x. It just stands for the line or the tangent line when you put x in. So that will give me an equation for that red line. Really, though, it's just point slope form. Do not go memorize this. That will make it difficult. Just always create it when we go do these. On the bottom third of your graph, what I want you to do, I'm going to grab the eraser here for a second. On the bottom third, so draw another line there to go to the bottom third of your paper. You're going to go like this. God dang it. Keep moving my screen. You guys, getting grouchy. All right, so go to the bottom third. Come on. There we go. When you're doing your approximations, if you look at this red line, you'll notice that when you find, say, a value right there on the red line, are you above or below the actual curve? Above. So your line is going to give you for this one an overestimate. But why is the tangent line above the curve there? Because over here, my tangent lines are below the curve. What word am I looking for? When are your tangent lines above your curve? Concave, yeah, it's the concavity. So you are going to be asked, is your approximation an overestimate or an underestimate? That's going to be a piggyback question that goes with linear approximations all the time. Are you finding me something that's a little bit too high or a little bit too low? And what did we just say that depends upon? Concavity. So let's just draw a little deal like here. If you're concave down, that means your tangent lines are above the curve. So your line equation is going to give you an answer that's a little bit too high. Algebraically, that means your second derivative, when it's concave down, what's your second derivative? Less than 0. Yeah, exactly. So I'm going to write that on here. All right, so if you can look at the graph and see it, well, that's great. But this would imply that you're going to have an overestimate. If at the point where you're drawing your tangent line, the graph is making a smile or holding water or equivalently concave up, your second derivative is positive. Your tangent lines live a little below it, so you are going to be giving me an underestimate. All right, so we haven't done anything yet. I'm just laying out the theory behind it. The theory is if you can get an equation for the red line, and if you stay really close to the point of tangency, your red line is very accurate for the curve. As you get farther away, it gets less accurate. We get the equation for the red line by doing point-slope form, which we learned in Algebra 1. So it's a lot of algebra. So what I want you to do next is, in that homework packet that I just gave you, let's go right here, actually. Go to this page in your notes. Go right here. We're going to start this with the easiest function in the world to graph, take a derivative of, and all that stuff, just so you can see the process. The process won't change. The only thing that's going to get harder as you work through your homework packet today is taking the derivatives. But your process won't change. So here's the theory. You have a function, and I gave you the easiest function in the world, just the standard parent function for a parabola. It says, find the equation of the tangent line. So go and maybe bold it right here. I want the equation for that line. We've been doing this since like week 2. Equation of a tangent line. All I need is a point, and this is going by 2s, I can tell, and this is going by 1s, because my point when x is 2 is 2 comma 4. All I need for the equation of a line is 1 point. You will always have that because they're going to tell you what the x value is, and then you can just shove it into the function. So that's my point. What else do I need for an equation of a line? I'm not even going to use any formulas. What else do I need? Slope. Yep, Ben, so let's put that on there. I need the slope. Calculus term for slope is the derivative. Where? Derivative at 2. Yeah, exactly, at this point, but it's the derivative for this is dependent, it's just a function of x, so I just need the x. So that's easy. That's an easy derivative to take. My derivative is twice x. So my f prime of 2 is just going to be 4. Really, I'm in Algebra 1 class right now, writing the equation for the line. Don't even use the formula with all that c's in it, because really it just comes from this. Y minus the y I know is equal to the slope there times x minus the x I know. What did I tell you they do for this one? They don't leave it like that. How will you see it? Yeah, they'll move the 4 over. So it'll look more like this. Y is equal to 4 plus 4 times x minus 2. And what did I tell you they'll call the y in a formula? L of x or T of x. I'm fine with the y. It's good for me. Now, this is what you're doing. You're using it to approximate f of 2.2. So right there is about that blue dot. You might say, I don't need to approximate it. You don't. You've got a calculator. Go do it exactly on your calculator. Just go do 2.2 squared. Because you don't really need to approximate it when you have it. We're just doing this for the process. Go do 2.2 squared, and what do you get? 4.84. All right, that's the exact value. I'm using the red line to get an estimate. Will mine be an over or an underestimate? Under. I can see it. The red line's living below the curve, but it's below because the curve is what? Concave up. It's concave up because I can see it, because I know it's a parabola, but if it's a function you can't see, then you would go take the second derivative. There's the first derivative, there's the second. It's positive. It's making a smile. Its tangent lines are under it. So I'm going to have an underestimate. So here's my estimate. I would say that f of 2.2 is about, it's exactly this, which just seems kind of weird. Why would I do this when I know exactly what it is? I wouldn't for this one. I'm just doing this for the process. So my approximate comes from my tangent line. I do 4 plus 4 times 2.2 minus 2. I'm living on the line, and I'm really close to where it is on the curve. And I believe if you do this right, it'd be 4 plus 4 times 0.2. I get 4.8. Is that pretty close? It's awesome, right? It's really close. It's just a little under. What would have happened if I used my line to estimate what happens at -2? Would it have been good? Oh my, it'd be horrible, right? So what makes it accurate? How close you are. Yeah, you got to stay real close to the point of tangency in order to get a really accurate estimate. So what we're going to do next, there's my scroller. Why couldn't I find it last time? I don't know, the world's messing with my head. This one right here in your notes, write this. So flip the page. This is on your homework packet. It's number 2. So just go to the homework packet and we'll go do number 2 together. Otherwise, you're going to end up doing the same problem twice. Again, this isn't a function I would normally do this with, especially if I have a calculator. I do not need to estimate f of 1.9 when I have a calculator and I can just do 2 divided by 1.9. But when the functions are ugly and I can't graph them, or before the days of good calculators, this was a very, very good skill. What I want you to do before we even start is take out your calculator, because we have one, and let's get the exact value of f of 1.9. Can you go divide 2 by 1.9 for me, please? It is exactly what? What do you got? What is it? 1.052. That's exactly what it is. We're going to go use this process to come up with an approximation. We know what happens at 2 because 2 is a nice number. And 2 is really close to this, so that's easy. So here's what I've got. I've got a point on the curve. It would be 2, comma, put it in, 1. Plus, actually, you should know what this curve looks like. Let's go throw it on there. Its parent function is 1 over x, so it's going to look like that. It's going to go through 1, 2, and 2, 1. It's going to look like this. All right, so what I'm doing is I'm going to where x is 2, and I know there's a 1. I'm going to use this tangent line. And as long as I stay real close to 2, just so you see a visual, it helps. All right, let's begin. I've got my point. What do I need next? You can go ahead and answer me. I know I'm recording. I said not to talk, but I can't stand it. All right, so go ahead. What do I do next? Slope. Yeah, let's go do it. So I'm going to need my slope. How do I get the slope of a line in calculus? I do the derivative. I want to find the derivative at what? 2. Yeah, perfect. I want to find the derivative at 2. So really, if you can take a derivative and you know point slope form, this is easy. Just don't memorize anything. Don't even look at the formula in your book. So I have my f of x is 2x to the -1. So my derivative is a nice one to take, a nice power rule. Negative 2x to the -2. So my f prime of 2 would be -2 over 4. It's gradually downhill line. Looks good. It jives with my picture. Now I'm ready to write an equation for my line. I'm not memorizing anything with L's and C's and primes. I'm just simply going to go back to Algebra 1 and do y minus the y I know is equal to the slope there times x minus the x I know. Am I good? Did I do the derivative right? Yes, I'm good, right? All right, next up, what did I say they'll do with that if you looked in the back of a book or if you Googled this? They'll add it over, yeah. So they're going to have 1 added over minus 1/2 of x minus 2. What are they going to plug in for x? When you're doing approximation, what am I trying to approximate it at? 1.9. So I'm going to try to squeeze it in here. F of 1.9 would be about what it would be on this line. So I go put a 1.9 in there. I subtract 2, I get 0.1. Half of that is 0.05. I'm going to be doing minus a minus, so it ends up adding it. Look at my approximation and look at the exact. They were close. Why is mine an underestimate? Because it is. Not much, actually. It's darn near perfect. Why is mine a little bit under, though? Concavity. Yeah, exactly. Or the second derivative, if you were to take, if you couldn't see it, and you had an uglier function, you would just algebraically take the second derivative. So if the first derivative is negative 2x to the negative 2, the second one would be 4x to the negative third, or 4 over x cubed, which is positive for all the positive x's. So you know you're concave up over there. All right, last one. We will do this one next. I'm just going to erase all this stuff. All right, so back to your notes here. We're kind of going back and forth between the two. I'm going to scoot this up. It's kind of a mess. One last one, and then we'll go do a couple in the packet. So now I've got another function. It's the square root function. And I am going to be looking at that at x equals 0, and I'm going to come up with a tangent line. So first of all, when you know what the graph looks like, go put a little grid of it up here. You know the square root function looks like that. It shoots out from negative 16 for this one, because that's what would make it 0. I am approximating it with my focal point of x equals 0, which gives me my point, 0 square root 16. Let's go put that on here. There is my function. I'm going to use the tangent line that hits at 0, 4 to approximate what happens on there. So again, easy question, over or under estimates? I'm going to have over. And if I had to explain myself, I would talk about it being concave down there or second derivatives being positive. It depends on if you're doing graphical analysis or algebraic. All right, so let's begin. I've got myself a point. Easy peasy, right? I need a slope. Booth, how do I get a slope? Take the derivative. Yeah, my slope in this situation is f prime at 0. So let's go take the derivative. If f of x is x plus 16 to the 1/2, then my derivative there would be 1/2 x plus 16 to the negative 1/2 times the derivative of the guts. Don't forget about that, by the way. On your worksheet, there's one where the guts are like sine x plus 2. So you need to do the derivative of the guts. Mine, the derivative of the guts is 1, so it's not going to do anything. But my derivative function is 1 over 2 root x plus 16. So what's the slope of my red line? How about Kyle? What's the slope of my red line? Yes, he's plugging 0 in here, and he's just using his slope formula at x equals 0. Awesome, 1/8. Once you get those, you're back into Algebra 1 class. You're not going to use the formula because it'll just mess you up, and you're just going to do point slope. Y minus the y, I know, is equal to the slope there times x minus 0. Or equivalently, y is equal to 1/8 x plus 4, or 4 plus 1/8 x. Are we good? Done? Let's leave the notes then. I want you to go to the homework packet. We're going to do a couple of those together just so you can see the difficulty bump up a little bit. I did easy ones just for process, but I wonder if somebody last hour's, oh, they didn't steal my key. Got it. All right, let's do number, not number 1. We already did number 2. We're going to go look at number 3. All right, on the back side. Number 3. I like this one because I want you to work with trig, and it's the one I talked about at the beginning of the hour. So find the linear approximation for sine x. So here's your function. Hey, Havana, ought one know what the graph of sine x looks like? Yes, thank you. Let's go do it. She's refusing to speak. I kind of like it. No, just kidding. Here you go. So let's do our sine wave, and technically it goes like this, but we're looking at it in at 1 radian. So we've got pi over 2 here. We've got our pi there. That's the function I'm approximating. Keep in mind, before graphing calculators, if you wanted to know what sine, cosine, and tangent were for the non-nice, like pi over 3, pi over 6, nice unit circle hits, that was difficult. So we are approximating, and we're going to use the tangent line at pi over 3, so that'd be less than pi over 2, probably like right in here would be pi thirds. So I'm going to use the red line to approximate values on the curve. So let's go take a look and do that. First thing I need is a point. Go ahead, help me out with the point. What x value did they say I'm using? Pi over 3, let's go do that. What's the y value there? Well, 100% sure, what is sine pi over 3? You should be debating between 2, either root 3 over 2 or a half, so think it out in your head. What is it? Thank you. We're at 3 over 2. Got to have a rock solid unit circle throughout all your calcs. There it is. I need the slope. And I'm going to use old-fashioned algebra M because that's really what it is. We call it the derivative. So I really want f prime where? Pi over 3. Yeah, let's go do that. Well, that's an easy one to take the derivative of because the derivative of sine is just cosine. There's one in this packet, though, that's got one you haven't done for a while, so let's bring it back to your memory. What's the derivative of tangent? That is secant squared. There it is. Thank you. All right, bam! She's got it. All right, so what is cosine pi over 3, 100% sure? 1/2. So I'm ready. It's as easy as that. My process isn't changing, and as long as I'm not trying to memorize stuff, if I've got a really good idea what's going on graphically, it's nice. All I do is y minus the y I know is equal to the slope there times x minus the x I know. This is what we call our tangent line approximation. It sometimes looks like either of those, but leave the y there. And then I told you what you'll see is I'll just move that over to the other side. So let's write it. Root 3 over 2. Phew. Plus 1/2. And now you're going to see kind of how silly this whole process can be now that we have calculators. Right? I want to approximate sine of 1. So f of 1 will be about, go to your calculator and go do that. Root 3 over 2 plus 1/2 times the quantity, 1 minus pi over 3. Crank the whole thing out on your calculator. And somebody tell me, because I don't have mine. I remember it's 0.84. All right. Now, what's the actual value? Sine 1. Go do that on your calculator. See what I mean? Do you see kind of how silly the approximation process is for you guys right now? I don't need to approximate it. I have technology that does it. What's the actual value? Go do it on your calculator. What do you get? I don't know. I don't have mine. What's sine 1 on your calculator? Make sure you're in radians, though. Point what? What's better? All that work or the calculator? Well, the calculator, obviously, because it's exact. Mine, I do believe this was 0.842 if you had done it, right? It's a little overestimate. Again, it's an overestimate, not because the sine function's concave down, because the sine function's both, but at this point, it's concave down. What do you think? Easy peasy? All right, we're going to do one more. The other one I want to do, I felt it fall, but I don't see it. Maybe I didn't feel it fall. Let's go look at number, the other hour. We did number 2 on the next page. So one more, and then we'll let you go work. Number 2, where it says let f be the function such that. If you really get it, you can just pick all of these apart. They're all about points and slopes. All right, number 2, f is a differential function such that f of 3 equals 2. Your brain should be screaming, and you should write down point directly given to you. It says, and f prime of 3 equals 5. What should your brain be thinking? So, exactly. M equals 5 there. Well, this is nice. Right, Havana? Or you're like, what? They gave me everything. Wait till the question, though. It's y minus 2 is equal to the slope times x minus 3. Equivalently, my y values will be 2 plus 5 times x minus 3. That will be a tangent line that approximates stuff. They want me to approximate a 0 of f. So be careful with that, because you know a zero's got to go in here. But a 0 of f, which one of these is actually 0? When you have a function you talk about its zeros, who's 0? Y, exactly. The zeros are the x values that give you a 0, those x-intercepts. So it's actually this one. So 0 equals 2 plus, let's just do 5x minus 15. If you go solve that, you'll get the answer that's circled there. By the way, I bet if you put a 0 in for x, that answer's there, but I'm not positive. What do you end up getting for this one? 13 fifths, 2.6, I think. All right, we're done. So what I want you to do is go to number 1. Some people finished it last hour. Most had 1 or 2 left. This should not take up much time. But what's still sitting out there? You have 25 minutes, it looks like. What do you still have sitting out there? That big packet, that's your big task. This is a small task. You might finish it before you leave. I'm going to leave the key sitting right up here so you can look at it.